Okay, so let's talk about application layer. So as you know, application layer is the layer sitting on top of all the layers, considering OSI or TCP model doesn't matter. Application layer is the most upper layer, basically the layer that the user is dealing with it mostly. So today we're going to talk about some protocols, okay, some specific protocol like HTTP, FTP, SMTP, DNS, and see how they are working. But the main goal is basically talking about the concept of application layer, implementation aspect of it, a little bit about client-server paradigms, what type of application model we're going to have. So, and some, as I mentioned, some important, basically, protocols in application layer. So you can see application as, for example, how can I say, it's a part of the network that runs on the user space, okay? Or running a network host in the user space. So you can have different type of applications. For example, in this figure that you can see, we have different switches, routers, users, servers here. There are some user part here. So basically, those application layer in the user side talks with the application layer in the server side. Or, I mean, it can be considered as a normal structure of the network and with like 5 layers structure here, TCP, let's say. So application layer basically defines the rules for message exchange. And let's talk about fetchless. I mean, not much really here, I tell you. So can you all hear me well?
Yes. Yes.
Yeah.
Okay, a moment, let me open this participation. Okay. So these are the important concepts when we are talking about the application layer, process, user agent, what is interprocess communications. So basically, process can be seen as a programs running within a host that can be considered our process. It can be within the server as well. That would be the server-side process. So within the same host, two processes can communicate using interprocess communication. Those type of rules for interprocess communication usually defined by OS, so it might be slightly different. For example, if you talk about Windows or Linux or Mac OS, it might be slightly different. So process running in different hosts communicate within application layer protocols. And when we're talking about user agent, it can be software process, it can be the interface of the applications. So for example, talking about user agent, those can be considered, for example, if you talk about the web, the user agent can be browser. When you're considering, for example, application like email, the user agent can be the mail readers. When you're talking about the streaming audio videos, the user agent can be considered as a media player. So these are just some definitions I wanted to talk about before going to more deep. So we have two, basically, not two. We talked about this before. Like we have two different, for example, communications. This is, I think we talked in 4th or 5th week. We mentioned it a little bit. We can have client servers communication, and we can have, for example, peer-to-peer communications where in client servers, the side is a client, then you communicate with the server in order to fetch some information. That can be client-server paradigm. Another was, if you remember, we were talking about, like, for example, peer-to-peer communications, something like torrent applications that all the basically parties that are all the sites and hosts can be considered as a peer to each other. So talking about client-server paradigm, the network has two parts, basically two pieces. We have client and we have server. So as you can see here, for example, there is a client and there is a server. So those applications process going to communicate with each other. So in client server paradigm, clients is the one usually initiate the contact with the server. So basically, client is the one that speak first. So typically, request service from server. It can be any type of service that you can imagine, like web. I don't know, HTTP, for example. You want to fetch some website. You can read some emails. You can even download some files. In this method, it can be all those requests can be from the client side, and the server basically provide request service to the client. Server is the one that provides you the services. Okay. So, for example, web server sends request, web page, you download the web page, mail server, or a lot of different applications. So when we're talking about really application layer, it's very straightforward because, and it's almost the most well-known layer for everyone, because that's the one we are dealing with basically, or because we're using network, that's the one we know the most. So in this, for example, structure application in the user side, this is the user side or client side, and this is the server. So it's just slightly different icon. So user send the request, then server replies that request. So this is the client server's paradigm. And if you remember in peer-to-peer paradigm, the difference was all the peers can provide service with each other. For example, if considering a normal peer-to-peer architecture, for example, I can be the one as a, for example, my laptop is connected to all your laptops in a peer-to-peer communications. So for example, my laptop can serve you certain files, or like if you're talking about torrents, or your laptops can serve as a server for me, like a provide me some services. So this is like all the systems are having a peer level of importance in that peer-to-peer communication. So continuing talking about the application layer, API is application programming interface. If we mentioned API, you heard the API all the times. Maybe you didn't know what it stands for. Is application programming interface. And what it does is basically defines interface between application and transport layer. And the socket is an internet API. So two processes communicate by sending data into socket, reading data out of the socket. The socket, you can see socket as a, if I can give some analogy, for example, you can consider your system as a one apartment with different floors. Each floor has different houses. Okay, so when the packet comes, it should know which process is calling, right? Which process was requesting this packet, because there are several processes running in our computers requesting different packets. At some point, your antivirus is getting updated while you're downloading some files, or while you are accessing FTP servers, or while you are streaming videos. You're doing all those things at the same time. So packets comes and goes to that socket that is specific for that packets. And that socket is specified to that certain process that is calling those data. So how does a process, this is not supposed to be here, so you're supposed to answer that, but how does a process identify the other processes within with which it wants to communicate is, as you know, based on the IP address. So IP address can be, for example, in that analogy that I mentioned, IP address can be the building, and the port number would be that particular door that requesting those packet or letter in that analogy. So you can basically consider IP address and port number in that manner. So last week you talk about basically with Juan, you work on transport services. transport layer protocols. I'm pretty sure you talk about TCP, you talk about UDPs, and what transport you already know that each layer provides services for the layer sitting on top of it and getting some packets from the layers sitting on down below it. So transport layers basically provide certain services for application layer. For example, data loss, timing, bandwidth. These are some examples. For example, talking about data loss, you know some application can tolerate some data loss. Not all of them, but some of them can tolerate data loss. For example, audio file when you are streaming music in Spotify, it's okay if there are few packets get lost there. It's not that a big deal. Or when you are streaming a YouTube video, if few packets get lost, you're never even going to notice that. So those, how to say, those type of application can tolerate data loss. But there are other applications or other type of file transfer that they cannot tolerate data loss. For example, when you're receiving emails, you want everything to come intact without any problem. You want to receive all the information. In that type of situation, you cannot tolerate any data loss. Or when you're dealing with, even for example, with HTTP, when you're fetching some information from a website, you're checking the news, no matter you're checking your bank accounts, okay, those are basically requires 100% reliable data transfer. Another thing is another services that transport layers provide is like timing. Again, some applications can tolerate delays, where some of them they cannot tolerate delay. For example, talking about delay, when you are streaming, you don't want any delay, right? You want to receive all the packets smoothly because you don't want to have any pause on your YouTube video. But when you are updating your email, when you're refreshing your email address, email like inbox, it can be some delay. It's not a big deal if there are like, I don't know, 10 millisecond delay to load your website. It's not a big deal. You can tolerate that pretty fine. So there are some applications that can tolerate, some of them that are not able to tolerate. Some of them require low delay, some of them are not delay sensitive. And talking about bandwidth is the same. Some application requires a very high bandwidth, while some other application, they don't require high bandwidth. But here, I have this mentioned. Okay, let me talk about this more. So for example, you know, for example, when you're streaming, let's say, a video from YouTube, the bandwidth that is required for it depends on the quality of the video that you are fetching. If it's HD, you require certain bandwidth. If it's full HD, if it's 4K, much higher, right? But anyway, at some point you reach a certain limits. Let's say if you have, I don't know, 50 megabit per second, it's pretty fine for fetching the 4K data. So you don't need more than that. That's the limit for application to use, okay? Or let's say 20 megabit per second your application going to use. But some other applications that we call them like elastic apps, they make use of whatever bandwidth they get. Okay, it's not depends. For example, 20 megabit per second is fine enough for me. I don't need more than that. For example, you are streaming full HD videos. That's all you need. You don't need more than that, even if I have 1 terabit per second internet connection. So can you think of any elastic apps? An application that make use of whatever bandwidth you give it? Any example? What type of application can use all your bandwidth? No matter it's 10 megabit per second, it's 100 megabit per second, it's 1 terabit per second.
Applications that help you download some software could use all the bandwidth.
Yeah, exactly. For example, when you're downloading a software, if you have 10 megabit per second internet connection, it's going to limit to that. If you are not having any other processes using the bandwidth, it tries to use all the bandwidth. if you give it like 100 megabit per second, then it's going to trying to use all that bandwidth available. For those type of applications, we call them like elastic apps, that they try to use all the bandwidth that they get. It's just some terminology, it's not that big deal. So this table shows certain applications with data loss, bandwidth, time sensitivity. For example, file transfer, data loss. You don't want any loss when you're downloading certain files. You want all of it to come without any problem. The bandwidth is elastic because you can use all the bandwidth possible, no matter how big is your bandwidth, but it's not time sensitive. In other hand, for example, real-time audio videos, you can tolerate some data loss. It's not that a big deal, but the bandwidth is not elastic, it's fixed. If you're doing audio or if you're doing video, for example, here it says max unit 10 megabit per second. Of course, now we know it's not enough. This is unit more if you wanna, I don't know, stream 4K videos, some case 8K videos. Or you can see different type, for example, financial apps, you don't want any data loss. It can be basically using all the bandwidth, some certain applications, but time sensitivity, of course, if you are, for example, dealing in a stock exchange, you don't want any delay, right? It's time sensitive again, but there can be some other financial apps that it's not time sensitive, okay, that much. So you can see that we have different type of things or different type of services that transport layer can provide for application layer. So you talked about this too last week, TCP, which is connection-oriented transport layer protocol. So, so for example, here you need a setup to be provided to happen between client and server. You know, it's TCP provides you with a reliable data transfer, while UDP is not reliable. TCP provides flow control, so a certain sender won't overwhelm the receivers. That type of service can be provided by TCP service, not by UDP. It provides congestion control, which UDP doesn't provide. But what TCP does not provide timing, minimum bandwidth guarantee, and it just guarantees the minimum bandwidth, doesn't guarantee the full bandwidth. While the UDP, you already know, is unreliable data transfer between sending and receiving process. It does not provide connection setup, reliable data transfer, flow control, congestion control, all those. And you already know that how to say, because it doesn't provide a lot of these type of services, it's more lightweight, right? So the question is, why to bother? Why is there a UDP? I mean, I think you already know the answer. Yes, Adalberto?
Because it's cheaper for some services that doesn't require those services. No?
Yeah, exactly. It's I assume when you're saying cheaper, you mean process in a process way, you know, like a how to say?
Overhead?
Pardon?
Less overhead?
Yes, less overhead. So because it does not provide a lot of services, so it has less overhead. That's why it can provide faster connections, right? So it's not that because it doesn't provide all these good things, we don't need UDP. We needed UDP at some certain applications. We already talked about that before. So this is some another certain, for example, few example of application layers with application layer protocol and underlying transport protocol. For example, for email, we can have SMTP. I'm going to talk about it a little. And we have TCP because we want reliable data transfer. Where for some streaming multimedia, it can be TCP, but usually it's UDP. Again, it depends. For example, internet telephony, it's UDP, or you can see different application with their requirement. So let's talk about now some of the protocols, specific protocols. The first one we're going to talk is HTTP or hypertext transfer protocols. You know already, you're using it every day. You know what is it? It's web application layer protocols. It is client-server models. This particular protocol is client-server because now you are a client, you fetch some information from the server. It's either email, if it's news, if it's your bank account. So we have two different protocols. For example, it is not, for example, we have one HTTP. This is the standard RFC 1945, the first version, but it's still updating. It's still improving. At some point, the new version came that covered some of the weaknesses of the first version. But in general, you have this HTTP request from the server, then the servers respond you with HTTP response. But it doesn't matter on what type of OS you're running on your system. It's PC, it's Mac, it's Android, it's iOS, doesn't matter. You have the same basically request response method. So we talk about that HTTP is using TCP, transport services. So what it does is the client basically initiate a TCP connections. Usually it happens through the port 18. You should be able, I mean, you should already be familiar with certain ports, like some familiar ports that are very well known. So server accept TCP connection from the client, then HTTP messages will be exchanged between the browsers within browsers, your browsers, in your client side with the information basically getting from the server side. And then after you've transferred all the files, required files, then TCP connection is closed. Another important things here is to know is TCP is stateless. TCP doesn't keep the state of the communications, okay? So for every file that you're fetching from the server, you're creating one TCP connections. So you have the, for example, you're uploading, you're browsing a certain website, okay, let's say news website, you go to, I don't know, whatever, like BBC. Then you open the BBC and there are a lot of pictures, videos, links, text, right? So all those things that are basically in that HTTP version 1 requires one independent TCP connection. So you make a TCP connection, you get text, another TCP connection, you get this file, that file, this image, that videos, okay? Because HTTP is stateless. So that's why server maintain no information about past client requests. So each time you are requesting certain files, you're creating one TCP connections to get that particular file. So basically, why it is like that? Because protocols that maintain estates are complex because they need to keep the past history. Okay, if, for example, server client crashes, their view of estate may be inconsistent. It might be reconciled. So these are, I don't want to talk about this much because then it goes through the distributed system concept. But anyways, isn't that easy to keep the state? It's possible, but then it would be much more overhead for the network for that particular protocol. So HTTP is stateless. So for example, this is an example. Suppose a user enters this URL, whatever, just imagine a URL, some school, like edu, some department, you're checking, for example, Department of Computer Science in Tech. It contains text, references to 10 JPEG images. So what happens is first, HTTP client initiate TCP connections with the server. I mentioned that it's used port 18, then HTTP server at host. Of this, the host that having this basic information, waiting for TCP connection at port 18, it accepts the connection. Then client send the HTTP request message into the TCP connection that already established. Then HTTP server received the request message from the response message containing forms response message containing requested object, for example, the first text or any of those images. Then HTTP server closes the connection, and HTTP client received the response message containing that HTML file. But what happens, I mentioned like here, like for example, in this particular example, we have 10 different JPEG images. So this process will be repeated for all that 10 images that contains in that web page. Because I mentioned it's a stateless connection. So imagine for all these files that a website has, and you are seeing when you're loading a website, you are creating one TCP connection, getting this file, terminating TCP connection, creating another TCP connection, request, respond, now send me this file, receive this file, close the connection. So you see it's very complicated process, or very process consuming process. So I'm going to talk about that a little bit more. So in this one, HTTP1 server parses the request, responds, closes TCP connection. So for each file or each object that you're fetching from the server, you need 2 round trip time data. You remember round trip time is basically a time that takes from the packet goes from the client side all the way to the server side and come back to the client side. So this is 1 round trip times. So the first round trip time is for TCP to make the connections, request the connection. The second one is to fetch the information. Then the connection will be terminated. So that's why each transfer suffers from TCP initially slow sending rate, because I have to initiate the connection, then I have to fetch the information. So that's why when we were using this, many browsers open multiple parallel connections in order to overcome that problem. So a browser could open multiple parallel connections, TCP connection, to get all the information at the same time. But that was non-persistent HTTP. For now, we have persistent HTTP, which is that is standard, as you remember, 1.5. So it's the same TCP connection server. You make one TCP connection to be the server. The server parses the request, responds, parses new request, respond, parses new request, respond, parses new request, respond. So it doesn't terminate after each request. That's basically persistent HTTP. For clients send requests for all reference object as soon as it received based on the HTML. Base HTML, sorry. So you're getting the HTML, then you request the image 1, image 2, image 3. You get all those image, files. You don't need to initiate one connection for each. So that's persistent HTTP. So that's why you need fewer round trip times. That means faster loading the information, faster connection, of course. So what I want you to think of, we are telling you that HTTP is stateless. So how, when you're signing into your bank account, okay, you check your balance, okay, then you can transfer to your friends, you can do a lot of things, okay? So how this connection knows you are the same person? This is a question from you. So anyone has any idea? So we are telling that TCP is how to say, stateless. It doesn't keep the state. It doesn't keep the past history. You how to say, initiating connection, terminating connections. So how your bank knows when you're signing into bank or when you're signing into your email, you can send, receive, refresh, delete. You can do all those things. How that knows it's still the same connection. It's the same person using this. Anyone has any idea? Can share some insight? Maybe I'm asking you bad, but I assume you know already. You are familiar with like cookies, sessions created in your connection in your browser. So those are basically the files that tracking the connections that you have while you're creating, for example, when you're signing in the cookie, the session files in your browser keeps track of this communication. So you're basically bank knows that this request coming from this person that is already signing. This request coming from this person that's already signing because the session is still active. That's how basically you can do a lot of things after signing into your email. You can do a lot of things. Now you don't need to sign in each time for each action that you're taking. So this is some example for TCP. Okay, that how it works. The request is basically those packets, for example, HTTP message format or request packet format. They are in ASCII. They are human readable formats. So this is some example, like real example that the GET message, the request line start with GET. Basically, you are trying to get some information. So if you just look at this piece of information here, you can see, you understand exactly what's happening. So they are like a human readable format. I don't want to spend more time here. So this is, for example, the response that comes from the server side. So you get this packet, the connection is okay, this is the date, this is the server, what last modified the time for that page, what is the length of the content, what is the type of it, and this header continues by all the data that you asked earlier from the server. So you can see they are in ASCII, they are basically human readable. You can read and you can understand what's happening. I'm pretty sure you're gonna experiment this with one. So I'm not spending much time there. So there are certain status code in HTTP. You're familiar with some of them for sure. You're familiar with 404, not found when you browse or when you're calling a link. You see 404 error. That means not found error. Those are basically predefined error codes for HTTP response. So for example, in here you see the code 200. It means the content is there, the connection is established, so it's okay. So request is succeeded. Requested object letter in this image that is sending from the server. So for example, this error 301, like 301, it means it moved permanently. The request object moved. There is a new location specified later in the message. 400 can be bad request, the request message not understood by the server. 404 is like not found. 505 is like HTTP version not supported. So you can see there are certain codes for response status that define in HTTP. So talk about that HTTP, you know, some of them, they required authentications to basically when you required authentication to access certain contents. So basically it can happen like this. You have two-side client server. You send usual HTTP request message. The server replies you with this code 401 asking for authorizations. Okay. Then you send the HTTP request plus the authorization code. Then server authorize you and respond you with the normal HTTP response message. Then for another request that you're sending, it's again same HTTP request plus authentication code, getting back the message. So that can be a normal, a typical client-server connections, okay, for a server that you requires to authenticate. So authorization credential usually is a password. It can be name, password, or whatever. So it's stateless. Client must present authorization in each request. This is what I was talking about. So you remember we said HTTP's or TCP's HTTP is stateless. So that's why client must present authorization in each request. So authorization can be header line in each request. If no authorization headers, if you don't include the authorization in the header, so the server refuses the access to that particular data. Basically, that's what I said. By having the sessions, certain cookies that generated in your browser, those state will be saved in that browser. And each time browser is requesting that this HTTP, it sends that authentication authorization information again to get to maintain that connection, basically the trust between the server, client, and server connection. So another things that I like to say is about web caches or proxy servers. So the idea is to satisfy client requests without involving original servers. So it's not that each time you request a website, you're directly accessing the servers. If that was the case, you would definitely experience very slow connection most of the times. If for each connection or for each request, you needed to go all the way to the main server and fetch the information. That's why we have these proxy servers or cache servers. So basically, what I can say here, for example, look at this example. You have two clients, two servers. So this is proxy servers. So this particular client have this HTTP request. HTTP request is not available in the proxy server, so it has to go all the way to the original server that contains that information. Then it comes back from the original server by the HTTP response packet, goes to the proxy server, goes to the HTTP response. Okay, so for example, for this client now, this HTTP request goes to the proxy server and come back from proxy server to the client. Doesn't go, for example, to this original server anymore, because those information is already cached and it's already available in the proxy server. So the proxy server does not need to get that from the original server. You definitely experience this in your local device. You know, the browser cache a lot of information when you're browsing internet. You know, the browsers, your operating system caching some information. Already you know that. But we have some cache server or proxy servers too that they are much more powerful, of course. So why we need to use web caching? The idea is the cache or the proxy server is much closer to the client than the original servers. For example, you can consider this this scenario where you have all these users, you have a cache server. So for example, it can be, let's say we are working in tech, and we have for example, institutional cache server inside tech. So if I'm going to browse Mi Espacio, not necessarily it's going to go all the way to, I don't know, main server. Let's say it's in Monterrey, okay? It's not gonna go all the way fetching some information from there because it's already cached in that proxy server. If we have, I'm not definitely sure we have it or not. But there are a lot of cache servers in your ISP, in your region. And now there are recent trends also that uses this more. For example, like I give you an example, like for example, talking about Netflix. For example, one movie comes in Mexico, it becomes viral. a lot of people start watching it, start streaming it. So not necessarily that particular movie going to be in the one server in United States or in Europe. Those type of information will be cached in a lot of servers in a lot of parts of the globes. Of course, the cache that is in Mexico or it's in Jalisco might be different with the one in Nuevo León, with the one in the Mexico, and those decision will be taken like automatically, smartly by different algorithms. For example, what type of information needs to be cached in Jalisco because people are looking more in Jalisco. Those are more access from there. So it's used a lot in order to fasten our to have basically faster communications. So the idea is it's closer to the users. That's why it's smaller response times. That data can be fetched much faster. And another idea is it decreases traffic to the distant server. So not for every particular information, you need to go to the main server. For all the users, get the information from the main server. And imagine if in that type of case, you have 1 or 10 main server, how busy that server can get if we don't have this web caching. Any questions so far? Is it clear what we're talking about?
Yes, teacher.
Okay. So that's web caching. So the name, the idea that they are working now, researchers are content-centric networks. Okay, so different contents are distributed in the globe differently. Not necessarily it can be uniform distribution. The content that I mentioned closer to Mexico might be way more different with the one that they're accessing people in Germany. Of course, pretty much makes sense to make those data more popular in Mexico, much closer to the Mexico. So that's the idea of caching or content-centric network, which is a trend in the last 10, 15 years. So another application is FTP or the file transfer protocols. You know that, for example, you have user at host, you have FTP user interface in your system. You have, this is a client side, this is a server side. So you have FTP user interface, FTP client server, client side. Then you have certain local files system. Then you have FTP server side, and you have a remote files in your server. And you access those files basically using FTP connection. So the idea is what it does is transfer files to or from remote hosts. It's again client-server models. Client is the site that initiates the transfer. Server is the remote host. So basically, the one, for example, I'm using now that we are here, we are working at house. I have a server in tech. That's another class students they need to use for their Python programming. So I use always this FTP in order to update the server, to upload some files to that so a student can access. So that's the idea with FTP. It uses port 21. For FTP, for secure FTP, it uses port 22. And this is the standard for it. So in FTP connection, when you generate FTP connection, you have two different connections. You have control connections, okay, which is a TCP control connections. Another one is another connection that is basically TCP data connections. So in this control connection, you basically exchange command response between client and servers. And in the data connections, it's that connection that you use for data transfer. I mean, you don't do this manually. It happens through the FTP, standard FTP application layer. But the difference between the FTP, for example, with HTTP is FTP server maintain the state. Okay, for example, current directory, earlier authentication. That's why when you form this connection, you can keep sending information because there are this control connection that is exchanging this type of commands, and then data connection that exchanging data between client and the servers. or the host and the remote host. So these are like sample commands and sample return codes for FTP. Again, it does the commands in the ASCII. For example, you have username, password in order to sign into the server. Then another command is list that returns the list of the files in the current directory. This RETR file name that is retrieves the files, or store file name stores the files. I mean, these are not, I don't ask you to remember these things. It's just an example how the commands look like in FTP connection. And the return codes is like, for example, this code 331, username okay, password required, I don't know, 125, data connection already open, file transfer started, and so on and so forth. It's not important, just an example that how might look like an FTP connections. So let's talk about another applications, which is, for example, electronic mail. So talking about mail application, you can have three major components. And you have a user agent. You remember, for example, in the first slide, I say user agent can be the mail, web mail that you're using. Then the mail server, you have the mail server, and then you have a mail, simple mail transfer protocol, or SMTP. So the user agent can be the mail reader, the one that you're composing, editing, reading your messages. It can be Outlook, it can be Netscape. Those are very old, actually. It can be Outlook, it can be Thunderbird. I don't know what you're using, Gmail. So those are basically that is the user agent. You can see here, for example, you have user agent, the mail server, user agents, another mail server, and all this user agent, another mail server, and these mail servers are in touch, communicating with each other through the SMTP protocol. So the mail server is basically, can be the mail box. I'm talking about these three major components: user agent, mail server, and SMTP. Oh, sorry. So the mail server is basically the mailbox that contains your incoming messages, not those that you haven't read yet or you haven't fetched in your agent. The message queue of outgoing mail messages can be there in the mail server, and also, of course, it's using SMTP protocols between mail servers to send email messages. So basically, again, it's client servers. The client is the one sending email, sending to the mail server. Mail server is the one receiving mail server. So it's again the client server connections. So talking about SMTP, it uses TCP to reliably transfer email messages from client to servers in use port 25. You mentioned that mail is the one that you cannot tolerate any data loss. So you're going to use, for example, TCP in order to guarantee you're receiving all the files without losing anything. So there are three phases for SMTP, like handshaking, transfer of message, and closures. So you can say this is the same thing with TCP connections, nothing much different here. As we mentioned, you remember for TCP, you need to establish the connection. You need to, then after establishing connection, one round trip time, for example, that was, we were talking about HTTP. HTTP uses TCP. So you need handshaking. Then you need to transfer the message after that handshaking was successful, basically. Or this handshaking here is like, can be greeting, or it can be like seen as like authentication. Then you transfer the messages, then you have the closure of the connection. So again, the command is in ASCII task, response is status code, and the phrases to reply this command message. So this can be a sample one. These are just imaginary things, okay, it doesn't exist. For example, these are the codes that is accessing these servers, hamburger.edu. This is the message. So these are just examples. I'm not going to spend time on this. Another applications is DNS or domain name systems. Are you following up, or you got lost what we're talking about? Okay.
Oh, we are following you.
Okay. So yeah, it's nothing really weird here. I mean, it's very straightforward. Even when you read NetAcad, you can see it's not much here. So anyway, so let's talk about DNS. You know, for example, when we're talking about people may identify using your name, social security number, passport number, I don't know, in Mexico, INE. All those numbers are basically identifiers for every single people that living in this country or the world. In the world, basically, there are certain informations. So for internet host and routers, we are using IP address. These are nothing new. And basically, but what this is how we know each host and routers switches in the internet by IP address. But what we use as the users, we don't use the IP addresses, we use the names. So when you are talking tech like that MX, you're basically requesting to see tech website, but you don't put the IP because it's not that easy to remember, right? You don't put the IP address of all the services that you're using on the website. You put the name. So that name should be translated to this IP address. So that's the job of domain name systems. How to say, converting the names that you're entering to the actual IP address of the servers. So it does basically map the IP address and name somehow. So domain name systems are distributed database implemented in hierarchy of many name servers. So it's not that, for example, one server sitting in one part of the world, and each time that you're putting the names, it's going to go to that server and translate to the IP address, and that IP address go to the original server that has that IP address. It's not like that. It's a distributed database in different parts of the world. Domain name system is a application layer protocol. So host, routers, name servers to communicate, to resolve names, involve all those. So, and something to note is the core internet function, but it is implemented as an application layer protocol. It's like IP address that is core internet functions, but it's not application layer. The domain name system is one of those few core things for the internet, but in the application layer. So this is a simple domain name system examples. So for example, you have a root name servers, you have a local name servers, and like another service that has the actual address. So you request, as a user, you're requesting the host, for example, serve Eurocom.friends, then this message goes to the local name servers. Okay, with this message. It doesn't find, for example, the IP address for this. It's sending it to the root name servers. Oh, sorry, not that it doesn't find the IP address. It's like it's returning you to the original servers that has that information. Goes to the root name servers, goes to that authoritative name server that has this website that you're looking for. Then the message will be replied back all the way to the user that is requesting that information. Clear? So basically what you need to remember is this is a distributed database. It's not just one server in one part of the world. It's a distributed database. Then you remember this application layer protocol. I remember when we had partial 1 exam, some people confuse this DNS DNS was one of those examples that I put that you could put in the table for application for transport. DNS was the one some people got confused, but this is the application layer process. And basically what it does, it maps the IP address with the name that we are entering basically in the browsers. What? Yeah, it's done. Okay, yeah, let me see, I don't want everything. Okay, yeah, so what we talk is like application services requirement. These are the things you take away from this application layer. Is different application requires different type of they have different type of requirement. When we're talking about the reliability, the bandwidth, delay, it might be different for different applications. You remember we talk about client server paradigms. This is not the only paradigms for communication. We have peer-to-peers too. Then we talk about internet transport service models. You already know about TCP, you already know about UDP. And knowing all this information, then we talk about certain applications, HTTP, FTP, for the mail, SMTP, for domain, DNS, and so on. So these are just some examples, not of course all the application layer protocol. It has tons of other protocols used for different purposes. You already know HTTP for sure. You know HTTPS, that is the secure version of HTTP. You know SMTP, DNS, you have FTP, and you have secure FTP, SFTP. Those are some of them that you might know, or they are very popular. Any questions from whatever we talked so far?
No, teacher.
Is it clear?
Yes.
Okay. So yeah, I'm going to share this with you. So there are certain YouTube video I put for different part of the things that we talk. If you want to check out more, you can check them. They are short video, like 5-10 minutes videos each. You can check and know a little bit more about that. Before this class, I was wondering, you remember in the beginning of the semester, I introduced you one book. Anyone ever read the book? So, of course not. Pardon?
What was the question?
You remember I introduced a book in the first day that I said it was not required to read the book, but I said if you're looking for a good reference, these two books are good reference books. So I was thinking, is anyone went to any of those references?
I went to Gonville in Tech, but I didn't find them, so I didn't read them.
Oh, yeah?
Yeah. There was like all of them I asked and they didn't have them.
Okay, I see. So maybe it was gone, but I'm pretty sure they are available. So it might be just not gone, borrowed by other students. That's what I assume. So anyway, before I finish this session, again, now you have to read the chapter 10. It's pretty straightforward, nothing much really now here. So yeah, read it. Then you already have the announcement in. Let me go back to the class. So no, just a moment. So I put the announcement in the canvas. So please just start putting the summaries. So I recommend you to put the summary right now because you just heard it takes you 2-3 minutes to write a paragraph, like 100 words. It doesn't take you much time. And that's the easiest thing you can do for easy grade that you might ever get from this course. So read the chapter 10 and do the quiz till the Thursday. The exam is till next week, Monday. So really, the whole idea is we did with most of the hardest parts to me was talking about transport, mainly IP address. That is maybe most difficult part to completely understand, especially the subnetting. But there are not really tougher, nothing hard remained in this course. I mean, the rest is like nothing. It's pretty much easy. So I hope you do better for the exam quiz.
Teacher,
Yes.
so the next week we will have our exam on Monday.
Exam?
Yeah, I hear you to say that. I don't know if I'm wrong.
The exam
from NetaCat.
exam of this chapter.
Ah, okay.
No, exam will be the same. Still, if I show you this, you can see my screen. Still, I'm sure. Yeah. So,
Yes, teacher.
So we are following exactly the same schedule. We are not changing anything. That's if I go to the calendar. So as you see here, we are exactly following this schedule. We are pretty much on time. Here, I told you talk about application layer. I didn't talk about transport layer. Why actually the transport layer in the NetaCat is pretty very much simplified. It's very simplified. That's why I wanted to talk to you 2 weeks about transport layer, but I decided not to overwhelm you because that's why actually I asked you about the books, because I wanted to cover transport layer completely from the book I mentioned. But it would be totally something that you wouldn't see in the NetaCat, so I thought it would be maybe overwhelming, especially considering all this situation we are dealing with. So I eliminated this. I bring the application layer in this week, but we are following exactly the same thing. The final exam is going to be these days, and we are doing this. Basically, we are following exactly with this. So another question is like you don't have still the final project, right? One more project. Do you have any pending project at the moment?
No.
Do you mean like in network?
Yes. This course, any pending project that you are doing with one at the moment?
No, right now.
No.
Yeah, okay. For that, there would be one more project that wouldn't be that big, but it would be one more project to do, basically to cover this one that we had basically initially planned in the schedule. So we are following exactly the same thing. So that's all of it from me. If there is any if there is any questions about the course in general, about the content, what we talked today. No? Okay, if not, then see you guys on Thursday. Okay?
Okay.
Take care.
Teacher.
Don't forget to read the chapters, chapter 10.
Professor,
Okay.
can you send
Yeah, for
us an
sure.
email with the name of the books? Maybe we can find them online or PDF.
Let me show you.
Or is it in page 1?
Yeah,
Página uno?
that's exactly
Ah,
what
okay,
I'll show you.
okay.
It's like in general information. No. Let me see where I put syllabus. No. I put it somewhere. Sorry. Oh yeah, these two.
Okay, great.
Yeah, I mean they're both good. I personally prefer the latter one, the second one.
Okay.
By Stalin. But if you're looking for a good, I'm pretty sure you can find it. I'm not saying you download it, but there should be.
Yeah. Thank you.
Okay, guys, take care. See
Thanks, teacher.
you
Have a
next
nice day.
week. Take care. Bye.
Bye.